Sorry, I don't have any news. So in this case, no news is, I don't know if it's good news. I have our department administrative officer looking. I kind of wonder if we should go ahead with the presentation. What does the committee think? Because the examiner had the thesis, and the formal examination is supposed to start at 1:45. So I don't know if the committee, I'll leave it up to the committee. Should we wait or?
I'm fine as long as the external examiner is fine.
Yeah, I'm good. I'm glad I've seen the presentation. It always has a different opinion.
Yeah, because in light of time, and then the external has to return back to 12. So if it's okay with the committee, we'll give another couple of minutes and we'll start the presentation at 1:15. Okay. Sorry.
No problem. Shall I try to wrap it up? The presentation.
Well, yeah, I mean, we can still, I don't know, it's condensing about 15 minutes, but I don't want
I'll
to
try to.
maybe focus more on the results. And
I'm sure we'll find out the full presentation.
Right.
I know the exam is supposed to start a quarter to two.
Yes.
But I'm sure we're.
Yeah.
I'm in no rush. I'll give the candidate to have the time.
right. So don't rush through.
Okay, sure.
Would you like to come in and have a seat? Because we'll have to close it. All this stuff. All right, good afternoon, everyone. Yusuf, do you want to come in? And if you could close the door, please, not completely. Oh, excellent. Thank you. All right, great. Thanks. All right, good afternoon, everyone, and welcome to the PhD thesis public presentation. It's my pleasure to introduce Amr Gaballah. And just a little bit about Amr. Amr did his undergraduate in Egypt in electrical and computer engineering, and he worked for a few years in Egypt before coming over here to do his Master of Engineering. And he finished his Master of Engineering, during which time he did his research project with me. And I was quite impressed with his analytical ability and his passion for research. So I was very glad when he decided to stay on as a PhD student. So for the past 4 years, Ammar's been working on this signal processing problem related to Parkinsonian speech and voice in terms of assessing it, as well as looking at ways to improve the Parkinsonian speech quality and see what engineering solutions we can offer and how we can measure their performance. So Amr, without any further ado, please give your presentation, and that'll be followed by a formal examination.
Thank you, everyone, and thank you for attending this presentation. Thank you, Dr. Parsa, for the nice presentation. My thesis is about the quality of the sustained vowel and the running speech for people impaired with Parkinson's disease, and methods of assessment of the quality and to improve the quality of Parkinson's disease. So this is the agenda for today's presentation. And with that, we'll start by giving a little background of Parkinson's disease. Parkinson's disease is the second neurodegenerative disease after Alzheimer's. It affects around 5 million people worldwide. There are 100 people impaired with Parkinson's disease, new 100 people impaired with Parkinson's disease every year, and there are 500 people out of 100,000 for the age group over 60 are affected with Parkinson's disease. There's no cure, and there's no cure for Parkinson's disease till now, and there is no definitive treatment for Parkinson's disease. This is why it draws attention to the research related to this disease and how the beneficial ways to fix the symptoms related to Parkinson's disease. Parkinson's disease symptoms include normally tremor, rigidity, and of the body, and it also associated with abnormalities in the speech and voice. And this speech abnormalities in speech and voice appears at 90% of people impaired with Parkinson's disease. And normally, Parkinson's disease affect the speech in terms of loudness, intelligibility, and quality. So loudness is the level of intensity of the speech, and usually people impaired with Parkinson's disease have hypophonia or reduced SNR, reduced intensity volume. This affects and leads to a blurring of speech components, which leads to a reduction in the speech intelligibility, which is intelligibility is how many words understood by the listener from the speaker's speech. All of this lead to a reduction in the quality of the speech or related to Parkinson's disease. So quality is an attribute that encompasses many characteristics such as smoothness, clariness, pleasantness to the listener. So this raises the need to develop methods to treat these symptoms accompanied with the speech of Parkinson's disease. The first and obvious method is the medication, and from medications, levodopa comes as the most prominent medication related to Parkinson's disease. It's the most effective drug in eliminating in reducing the symptoms such as rigidity and body tremor. But it didn't have this effect on the speech. It's not consistent. It's not consistent solution. It doesn't have long-term effect on enhancement of PD speech. This raises the importance of other solutions such as speech assisted devices, which include the first PD speech amplifiers. PD speech amplifiers are usually amplifiers that are used to raise the intensity of speech of the speaker, of the person impaired with Parkinson's disease, especially in noisy environments. These amplifiers are not benchmarked in attributes of their performance of enhancing the intelligibility and the loudness and the quality of the speech. Other type is the portable body worn devices. Portable body worn devices are usually devices that utilize the use of sensors that attach to the human body parts, especially sensors that attach to the larynx. An example of these devices is ambulatory phonation monitor that is developed by Borsky and others. Although these devices don't utilize the use of a microphone, and this will lead to these devices cannot measure the SNR performance. So we need to assess the quality of these devices' performance and how they enhance the quality of Parkinson's disease. There are methods of assessment for the quality of speech of Parkinson's disease, and the first and the obvious method is the subjective measurement of the quality of PD speech. And as this photo suggests, it depends on utilizing many listeners that listen to the speech and give their subjective judgment on the quality of the speech. The quality is calculated as a mean opinion score of their subjective opinions. Although this method may look at the standard and the gold standard for measuring acoustic attributes such as quality, it's not efficient in terms of cost and time. This raises the importance of the going another way, which is objective measurements of PD speech. Objective measurements of PD speech are simply utilize the use of the previous mentioned subjective scores to develop a model that is capable of detecting and measuring the quality of speech automatically without the need of any human interface. So this machine learning algorithm needs a training database that has a known quality scores, and need to extract some acoustic features, some physical features that by using them will represent and applying them to a machine learning algorithm. This algorithm is capable of extracting a quality score to measure this quality attribute. So let's talk about these acoustic features a little bit. So there are traditional acoustic measures that have been mentioned before in the literature review for especially in measuring quality for sustained vowels, and they include harmonic to noise ratio, which is the ratio between the periodic and the aperiodic component of the signal wave. Cepstral peak prominence, which is the difference between the peaks of the cepstrum and the linear regression function of the cepstrum. Jitter and shimmer. Jitter usually measure the reverberation and the change of the fundamental frequency across frames, while shimmer measures the change of the speech intensity. Other group of features include filter bank-based features, which include MFCC and GFCC. So these three group of features usually perform on mimicking the performance of the ear cochlea, of the human ear cochlea, by applying a bank of filters. The difference between these two features, the first one is applying the Mill filter bank, which is a triangular filter bank, while the other one is applying ERB filter, equivalent rectangular bandwidth filter bank, which has more natural response and hence expected to have higher performance in detecting the quality than MFCC. Third group of features include speech reverberation modulation energy ratio, SRMR, and modulation spectrum area mode A. So these features usually depend on extracting the envelope of of the speech wave, and measure the change between the low-level components, which in the change of energy between the low-level components, which include the speech component, and the high-level components, which contain the noise, the background noise. This ratio is a representation of the quality of the wave vector. And finally, linear regression-based features, which include the LCQA, or low complexity quality assessment. It depends on extracting linear prediction coefficients to code that is usually used to code the signal, and then assess some speech features, including spectral dynamics, spectral centroid, and then extract the statistical changes. The statistical changes that include mean variance, skewness, and corpuscle to represent the quality of the Parkinson's disease. So, as mentioned, we need a machine learning algorithm to extract the quality score from these acoustic features. Machine learning algorithms are used in this paper include support vector regression and Gaussian process regression, and deep learning, which depends on the neural networks, which is used nowadays in many applications in artificial intelligence. And the role of this machine learning algorithm is to make the machine learn the features and then perform as a human to assess the quality. We need that sometimes that we have the effect of overfitting, or our model is capable of predicting the quality for the training data set, but it's not generalizable or cannot be used to detect future waveforms. This overfitting has methods to reduce the number. It's related to the number of features and the dimensionality between features. So we have two methods to reduce this overfitting effect. The first one is principal component analysis, which is usually used to extract represent the features in another dimension using the eigenvalues, and hence reduce the number of features applied to the machine learning algorithm. The other method is feature selection and reduction, which is usually we have the set of features, and we want to reduce the number of features, select a subset of these features that are more representative, which lead to more representative of the quality, and which leads to more representation of the quality in the machine learning algorithm. So let's state our problems here. First problem: most studies are based on PD study the classification of Parkinson's disease, meaning that they study whether this speech waveform are for a Parkinson's disease a person impaired with Parkinson's disease or not. But we think that there is a clinical importance in studying and assessing the quality of the perceived quality of speech. It's of high importance to clinicians and people and physicians to assess the quality during the course of the disease, and hence study the progress of the disease and its effect on speech. Another thing is that most studies are focused on assessing the quality of sustained vowel samples instead of assessing the quality of running speech. Running speech is sustained vowel. Running speech is more used in daily life more than sustained vowels, and hence there is more importance in assessing the quality of Parkinsonian running speech more than assessing the quality of sustained vowels. And there is current literature lack the application of state-of-art machine learning algorithms such as deep learning and neural networks to the features, and hence we are applying in this study deep learning to extract the quality of Parkinsonian speech. There's also a need to transfer the effect of treatment outside the clinical environments instead of applying these treatment methods in the clinical environments. And when the patient go outside the clinic, he loses this improvement. So there is a need to a solution that accompanies the patient during his daily life. And in this study, we are presenting a new device to enhance the attributes of Parkinsonian speech, which is portable, and the patient can use it during the course of his daily life. So let's start with our first study in this research, which is assessing of the quality of Parkinsonian sustained vowels. While running speech abnormalities appear at later stages of the course disease, voice abnormalities appear at early stages of the course disease, and hence there is importance in detecting these abnormalities and assessing how it affects the speech attributes of the voice. There is also a need to assess how the medication levodopa affect the performance of the voice, sustained voice for people impaired with Parkinson's disease, and how it helps them, or whether it helped them or not. There's also need to develop objective metrics that can automatically assess the quality of sustained vowel without the need of human interference. Data, so we are using here subjective data from collected by Diane Sparrow and Dr. Scott Adams from the School of Communication Disorders at Western University to test them and to analyze them and to develop the machine learning algorithm that we are using to assess the quality. So let's for the description of this subjective database. The database included samples collected from 51 Parkinsonian subjects. These Parkinsonian subjects were the data were collected from them when they were on the medication, and after 24 hours they were off the medication, and to assess the quality. It also, the data included data collected from 10 healthy control subjects who served as a control for this experiment. So the total database included 113 samples for the test. Subjective assessment of this database was done by three listeners that evaluated the voice sample subjectively and give them opinion scores, and hence the subjective scores for the quality. Features extracted from these databases that were used to assess the quality objectively included traditional acoustic measurements such as jitter, shimmer, HNR, and CDP. In filter bank, we used 60 GFCC, which included 60 features extracted from each web record. And also modulation-based features included SRR and Mood A. Linear prediction features are LCQA, which are 40 features extracted from each voice record. Machine learning algorithms were used here are first linear regression and support vector regression. When we discuss the results of the subjective analysis, we noted that people who come with high quality before the experiment, when they are off medication, and when they are on medication, the levodopa medication doesn't have such statistical enhancement in their quality. But people who come with already poor quality of voice related to Parkinson's disease, when they are on medication, there is an enhancement in the performance of quality of their voice. So for objective metrics, we have two groups. We have the objective metrics that include, each objective metric includes only one feature, and hence we are measuring the correlation between the values of this feature and the subjective score. And we have here that HNR, harmonic noise ratio, has the highest correlation value between the subjective and the objective score, that reach 0.59. This is the scatter plot between the subjective scores and the HNR scores, and this is the scatter plot between the subjective scores and the CPP feature. When applying machine learning algorithm on the extracted features, first we have GFCC and LCQA for linear regression and support vector regression. We have here that we noticed that LCQA for support vector regression had the highest for the test data set has the highest correlation value and the least overfitting. When we applying the PCA model to reduce the overdimensionality between features, we are noticing that also the values of the linear regression of the LCQA and the SVR is near, but there is a drop in the correlation value. Hence, we are using the reduced method, which provided us with 0.80 and for the test dataset and 0.81 for the training dataset, which we are provided with 0.66 for the LCQA using SVR and 0.66 for the LCQA for the training dataset, and 0.75 using linear regression for both the training and the test dataset. We are here developing a new objective metric that we are incorporating features from LCQA and Mod A and SRMR together in one objective metric to assess the quality. So there is high overfitting when using linear regression, but when we are reducing the number of features from 43 to 16 using the feature reduction method, we have here 0.81 correlation value for both the training dataset and 0.80 for the test dataset with minimum overfitting effect. This is the scatter plot of between the subjective scores and the objective scores for both the training dataset and the test dataset. And this is a combination of the scatter plots of the test training and test dataset together. So, as a summary for this study, analysis of subjective scores showed that there is a significant enhancement of levodopa in enhancing the quality of voice for people who already have poor quality, while this effect is not clear in people who have high perceived quality. We developed a combined metric that incorporated acoustic feature from LCQA, HNR, and CPP. The highest correlation value we got is 0.81 for both the training and the test dataset. But as we mentioned before, there is a need to assess the quality of running speech more important than assessing the quality of sustained vowels. This leads us to the second study, in which we evaluate the quality of running Parkinsonian speech. So this running speech is more ecological and more valid option for assessment than sustained vowels, and there is a need to assess also the performance of amplification devices when used with running speech in terms of how it affects and how it enhances the quality of the running speech. So the description of the database was as follows. We have database the subjects samples were collected from 11 Parkinsonian disease subjects and 10 controls. They were collected at different background noise levels. So each patient and each control give a recording at 65 dBSPL background noise and the presence of no noise at all. And each person gives his speech under these previous conditions using all of the speech 7 amplification devices that we are assessing, in addition to not using an amplifier at all. This led to a formation of a database that contained 672 samples. This database was collected by subjective database was collected by Monica Andrita and Dr. Scott Adams from the School of Communication Science and Disorders at Boston University. So the feature extracted include CPP, GFCC and MFCC, SRMR and Mod A, and LCQA. Machine learning algorithms used here are linear regression, support vector regression, deep learning, and GPR, Gaussian process regression. So in analyzing the results of subjective scores, we noted that there is a statistical effect on the type of the speech amplifier, on the quality of the perceived, on the perceived quality of the running speech, and there is also an effect of the background noise level on the perceived quality. It's clear that when we have high background noise, there is a clear drop in the quality scores, and there is also a difference between the performance of each amplifier in enhancing the quality of the perceived quality. So this table concludes the features, all the features extracted from all the objective metrics extracted from the database. We have here that GFCC has a high correlation value for the test data set, and but this, when we are applying the reduction feature method, GFCC doesn't enhance that much, but we have here other objective metrics like LCQA and LCQA that had enhancement when applying the feature reduction method. This is the scatter plot between the SRMR and the scatter plot between the subjective score and the unmapped SRMR objective metric, while this is for the mode A. This figure shows how we select the features from the database. We are selecting the minimum number of features that achieve the minimum difference between the mean square error for the training and the validation database. And this expressive number, when we use this feature reduction method, lead to enhancement of the generalization of the machine learning model, and will lead to reduction of the overfitting effect. This scatter plot shows the scatter plot of the subjective scores versus the objective scores for both GFCC and MFCC, and when applying reduction method. As mentioned before, there is no big enhancement in the GFCC method, but there is enhancement in the performance of the MFCC. We also developed here a combined objective metric with incorporated features selected from the GFCC, LCQA, SRMR, and mode A. We reached a correlation value of 0.85 between the subjective and the objective scores. It is noted that when we plot the scatter plot, there is a certain bias here at the test data set. We think that this objective metric is not capable of detecting the quality for the low quality, the quality at low levels. So to enhance and reduce the effect of this bias, we added a zero quality quality speech records to the database to make the model capable of detecting low quality scores, and this bias effect is reduced now at the test dataset after adding the zero quality speech samples to the training database. So, analysis of subjective, as a summary, our analysis of subjective analysis showed statistical significance of the speech amplifier type on the perceived quality. And the combined metric developed was incorporated feature from GFCC, CPP, LCQA, SRMR, and mode A. And the highest correlation value for the combined metric was 0.85 for the test dataset. But this raises the need of a system that can be used outside the medical environment to accompany the participant and lead to enhancement in his speech attributes. This leads us to the third study in this research, which is introduction of a new speech-to-noise feedback system that can be used to help patients in their life. So the motivation for this device is to give, as mentioned before, give the patient ability to transfer the treatment outside clinical environments and develop a wearable device that they can use, especially in noisy environment, to enhance their SNR in background noisy environments and enhance their speech attributes. So the mathematical model is as follows. We have the signal, we have the received signal that include speech component and noise component. We are depending on the device is collecting 1 second of data. We have here, we are depending on the measurement of the noise of the previous sample. When the device is detecting that, there is no speech in the recording, in the recorded wave using the sensor attached to the larynx, so it doesn't go through this process and assign the SNR to a fixed value of -20 dB. But when it detects that there is a speech component, it uses the power measured for the previous frame as a noise source and measure the power contained in this in the current frame and calculate the SNR of the signal to noise ratio in this acquired frame of data. This is a block diagram of the hardware design of the system. We have here an accelerometer sensor that is attached to the larynx of the patient that is able to detect if there is speech coming from the person or not. We have one right and one left microphones attached to the head of the patient. All of that is attached to an Raspberry Pi embedded system to analyze the data. There is audio. There is audio alert system, audio like through speakers attached to the patient that alert the patient when his SNR level go below a desired level. And there is also a visual display to show the SNR levels. This is how the patient is using the device. This photo is for the microphone, the main microphone that are in these black boxes and attached to the ear. This is an accelerometer that is attached to the larynx to sense the presence or the non-presence of speech. This is the collected device, which is stored here in this bank. This is a flow chart of how the system works. So as mentioned, the system is collecting 1 second of audio data and then calculate the power of the power contained in this frame and sense if there is speech in this frame or not. If there is no speech, this power measure is assigned to the noise level and repeat the loop. If there is speech, the system calculates the measured signal to noise ratio and give the patient 5 seconds if his SNR is below the desired level. For 5 seconds, it plays an alert to alert the patient to raise his voice in this noisy environment. And then if the speech, it goes to collect the second frame, or it ends the recording and generate a report of the measured SNR. This is the visual display taken as a snapshot for the visual display for the left microphone and the right microphone. We have here, are the noise level measured from the left microphone, and this is the noise level measured from the right microphone. So we wanted to test the performance of this device and how it helps the patients in a lab environment. This is the lab setup. We have the participant wearing the device. We have two noise sources from the right and the left that playing bubble noise at different we measured at no noise and at 65 and 75 dBs. We have a microphone that records the data and play as a listener that's connected to PC to collect the data for analysis. So this waveform, this is the audio waveform, recorded audio waveform, and this waveform is coming from the sensor attached to the larynx, and these are the measured SNR values. We noticed that the larynx is following the performance of the speech, and hence give good results for estimating the SNR for the speech. To analyze first the patient did each patient did recordings of sustained vowels, and we used the quality assessment method the combined methods to measure the quality for that mentioned in the second chapter to assess the quality of the sustained vowels. We noted that there is some enhancement in the quality at 75 dpSPL without using the device, and this is when using the device. So there is an enhancement. This enhancement is more clear in improving the SNR values for speech tasks. Each patient had a task of repeating sentences, reading a rainbow passage, and engaging in a normal conversation. There is a significant enhancement, especially in noisy environment, when there is a 75 dBSPL noise in the SNR level, and hence this will lead to enhancement in the intelligibility of the speech tasks. And this is the assessment of the quality of running speech using the combined model developed in chapter 3. We noted that the enhancement is not in the quality is not that clear due to the high background noise, and so there is an enhancement, but it's not significantly statistical as the measurement of SNR and intelligibility. We wanted to also measure the effect of using a binaural microphone from the right and the left instead of using one monaural microphone like the other literature. And we noticed that in measuring the SNR level, there is an enhancement of the SNR when using a binaural microphone from the right and the left instead of using one microphone in all speech tasks. And this enhancement is not clear in the rainbow passage, but it's clear in the sentence repeating passage and the conversation passage. And we think this is due to especially in the conversation, due to the interaction between the facial expression on facial expression between the talker and the speaker led to some enhancement, led to more effect of the conversation more than the rainbow passage. So as a summary, this new device aimed to enhance the SNR and special intelligibility and quality of speech. The accelerometer used in this device, which is more efficient in terms it has digital output instead of analog output, led to enhance the setup and the configuration of the hardware. The device was tested under different noise conditions to test the performance of intelligibility and quality and SNR, and it is found that the device enhanced the speech attributes, especially in noisy environments. As a conclusion, these are the main contributions of this study in terms of assessing the quality of sustained vowel. A new combined metric was developed that has a correlation value of 0.81 for both the training and the test dataset. In terms of assessing the quality of running speech, we have applied a deep learning, which a neural network that has applied to a combined model, led to a database that has correlation between the objective scores of 0.85, and a new device system was developed that is more efficient in terms of hardware and software, other than previous device mentioned in the literature, and it led to enhancement on of the speech attributes, including quality, intelligibility, and SNR, especially in noisy environments. It is noted that there is this study lacked the investigation of objective measurements of loudness and intelligibility, although they are highly correlated with quality. But we think that there is a future study, including the objective assessment of intelligibility and loudness, will lead to a significant impact on the clinical environment research. We need a larger data set. Of course, when you're increasing the data set fit to the machine learning algorithm, it will lead to the enhancement of the results obtained from this machine learning algorithm. And the device, the new developed device need to be investigated. Its performance need to be investigated outside lab environments, in car environments, in street environments, and in daily based environments, engaging environments. And it is noted that there is a limitation related to the device, that it's not capable of. There is a limitation that it's measuring for the noise reference, it's measuring for the previous power in the previous frame. So in severe varying noisy environments, there is the device measuring the SNR will lack some accuracy in measuring these SNR values. So this sums up my presentation for today. I would like to end by thanking Dr. Vijay Parsa, my supervisor, for his endless efforts through this 4-year journey. I learned him many lessons that I will carry for the rest of my life. I want to thank my family, my wife, my mother. My father is not here, he is following us. And I want to thank everybody from all my colleagues in Electrical and Computer Engineering Department. It was the honor of my life to know all of you, and to every person in Electrical and Computer Engineering Department, in National Center of Radiology, and the School of Communication Disorders. Thank you, everyone, and I'm happy to answer any questions you might have.
Thank you. I'm not sure the chair is here yet. Oh,
Yes,
sorry.
sure.
I'm sorry. I completely.
I snuck in.
We started a little late, and I'm not well.
Yeah.
Welcome.
Thank you.
Is it okay if we take a couple of
Of course,
questions? If there are
course,
any?
definitely.
Are there any questions for Amr from the audience? No? Oh, okay.
Yeah, thank you for the nice presentation.
Thank you.
Just I'm wondering what kind of noise have you used for your analysis?
So we used a Babel multi-toker noise, which is the worst, the most severe condition for noise. It's like the Babel noise is like a combination of multi-tokers that speak together, like you hear in airports and other environments. So this noise is not consistent, and we have and it's not stationary. And this was the worst case scenario to analyze the data in.
I haven't heard about it, so I wonder
So
what
it's
kind of noise
like we are having it's the type of noise that you hear in airports and environments. Like you have several tokers talking simultaneously, and so the sum is a noise that is not understood, and this noise is not stationary, and this is the worst case scenario. So apply the worst case scenario to assess the performance of the device.
Thank you.
Sometimes you hear that in cafeterias, or you're walking around a crowded restaurant or cafeteria.
It's kind of background.
Yes.
That's right. So it's non-stationary. It's problems. Thank you. Any other questions? All right. If not, thank you, Amr, again. And we'll move on to the formal phase of your defense.
Yeah.
And the chair will preside from now on. There are some goodies. If you guys want to take some, please go ahead. And then,
Do you want a bit of a break? We'll certainly just
okay.
say hi to your family.
Yeah.
Yeah.
Thank you.
Bathroom and then, yeah, might as well.
Here in London?
Yeah, I'm still here in London. Kids.
So it's
Hi.
external?
Good to meet you. Good to meet you. Where have you been from?
Okay.
Not too far. Yeah. Oh, thank you very much. That's not necessary. Thank you.
My son is finishing up his 4th year in mechanical engineering here, so I know the drive on the car one.
Sure. Is he here now, or is he back home, or doing some summer work?
He's taking a little bit of time off. Sure. Some of it will be back
Okay.
in a week.
Yeah.
So you don't have any laundry to take back with you?
No. So what department are you from?
Actually, psychiatry.
Okay.
So it's our grad studies people sent out a plea a few weeks ago.
Yeah.
Sure.
Well, the external, the internal, external can be from anywhere. Yeah.
So it's the same system too.
Yeah. Well, in this case, I'm chairing, so it's timekeeper.
Yeah.
I can. We hope.
Yeah. It's interesting because every university is slightly different. I'm not used to not have the advisor.
Oh, ask questions. Yeah.
I know. Sometimes you just need that little question.
Yeah, just
Okay.
even make them feel comfortable.
Yeah. However.
Yeah, well, I had done my PhD at York, and it was the same sort of thing. Supervisor got to ask questions, and it would tend to be a fairly easy one, but it would set you up to increase your comfort level. I should introduce myself, everybody. I'm Martin Heisel. Nice to meet you.
Pleasure. Nice to meet you. Silence again.
Hi, good to meet you.
Yeah, sorry. I need a plug once.
You have a slightly older one in mind, and it's amazing how the battery life does over time slowly get worse and worse.
I was on a flight to the US to a conference a few years ago, and I had an iPhone at the time. And we were, I think, held up in Dallas. There was bad weather. I guess they've had major accidents there with bad weather. So if there's any inclement weather, everybody. So we were all delayed in the airport for hours. And it seemed like most people had iPhones because everyone was running around looking for an outlet to plug it into.
So I'm going to sit at the end. If it's
Yeah, wherever you're. Not to worry.
Shall we start?
Yeah, I guess we should wait for him to come back. Because, we haven't sort of officially asked him to step out. He's just taking a break. So we'll bring him back next time.
Martin Heisel, nice to meet you.
Yeah, please. I was saying we're bringing you back in just to kick you out again. So what? At this point, I imagine, have you had an opportunity to meet